Hey, Torbs, thank you very much for your work with the SAC over the last 2 weeks. I'll get started on marking that sometime soon. However, in the meantime, we are going to move on to our topic of antiderivatives, the integration on chapter 7. So that's going to be our introduction exercise 7.1 on the antiderivative. This is from page 16 to 18 of the calculus booklet, so please make sure you have that out while we go through this. Alright, so let's start looking at the idea of antidifferentiation. So we're focusing on something first called the indefinite integral. So the idea is to say that if we're antidifferentiating, we don't know the exact value or the exact function until we have what we might call a key point, an anchor point, something to keep it in place. For example, if I have something very basic like x squared, I can differentiate that to 2x. There is no what ifs, maybes. It is 2x. Easy. But if I give you something like 2x, and I tell you to anti-differentiate it back into the original equation, well, you might end up with x squared. You might end up with x squared plus 1, x squared plus 2, or whatever it is, and no matter what, it's impossible for us to get an exact answer unless we know more information. So we'll get into that a little bit later, but today we're focusing on the idea of the indefinite integral. You can do that reading yourself if you'd like. So the rules to anti-differentiation, this one's right here. This one right here is what we're focusing on. So the idea is that if I have x to the power of n, for every time we anti-differentiate, we're going to increase the power by 1 and divide all of that by the power that we have that's new. It's the direct opposite of our differentiation. So differentiation, we bring the power down to the front and then minus 1. We're going to do the opposite, we're going to plus 1 and then divide it instead. These adding, subtracting, multiplication rules are the same as you would be expecting per usual. Let's move on. So, example 1, find the general antiderivative. This one's pretty straightforward. All we're looking at is applying the same rule as above. So, again, it's going to be 3x times to the power to the power of increasing that up by 1. So it's going to be 6 over 6. So we're dividing by our new power, which of course gives us an answer of x to the power of 6 over 2. Pretty easy. Of course, something like this would be the same thing as our differentiation in terms of step by step. So that becomes 3x squared, but that's cubed, to the power of 3 plus 4x to the power of negative 1. Note that negative 2 becomes negative 1. Divided by negative 1 plus 3x to the power of 1 over 1. So 3 becomes 3x, which simplifies to an answer of x cubed minus 4, and I'm going to write this properly as 4 over x plus 3x. Don't forget your notation here as well. Okay, so don't forget your antiderivative sign and then your dx as well at the end, making sure that that reflects what variable you're working with. Same thing for something like this. I'm going to jump into example BII. If I'm giving dy dx, we can do anti-differentiation to find y, where y would equal to the anti-differentiation of x to the power of 3 quarters plus x to the power of negative 3 quarters, of course dx, which you would get 4 times x to the power of 7 over 4 over 7 plus 4x to the power of 1 quarter over 1 plus c. Don't forget your plus c's, which I definitely forgot here. Please include your plus c's as well. General antiderivative, you must include your plus c's. If I ask for an example of an antiderivative, you don't need your plus c's. But in this case, general antiderivative, always include your plus c's. Of course, this would simplify to 4 over 7, x to the power of 7 over 4, and then plus 4x to the power of 1 over 4 plus c. An example of a worded problem, or more of a worded problem with this, is if we're given the gradient and we have to find the equation of this curve. So, as I mentioned, we can't find the exact equation unless we have additional information. In this case, we do. It is this one. So, we're going to write 2x, we're going to write dy dx equals 2x. Of course, that's at a specific point. I'm going to anti-derive it, so that becomes y equals to 2x squared over 2 plus c, which of course gives me y equals to x squared plus c. We substitute the point of negative 1, 4, which gives us an answer of 4 equals to negative 1 squared plus c. Of course, c would equal to 3. So therefore, we have y equals to x squared plus 3. There are two minor concepts, or two other concepts I need us to look through for this exercise. The first one is focusing on our polynomial values here. If we have a polynomial that's in the bracket, just like we're applying our chain rule, if we have something like this, it ends up being a 1 over a, so our coefficient of the x, multiplied by our increased power, our original function, with the increased power again, plus c, where r does not equal to -1. You'll note that if this value right here equals to -1, you end up with 0, and it just doesn't make sense. Right? So there's a different rule for that, but in the cases where we don't have -1, this is the rule we apply. I'm going to jump into an example for this one, and then go back and look at an example for the other ones. So we're looking at example 4a, with the general antiderivative where we have the power not being 1. So I write this as an antiderivative of 3x plus 1 to the power 5 dx equals to 1 over, and I'm going to write the multiplication of our first coefficient by the power increased by 1, which is 6, and we get 3x plus 1 to the power 6 plus c, which gives us an answer of 1 over 18 multiplied by 3x plus 1 to the power 6 plus c. The second example, we're going to end up with the antiderivative again, dx, where we have equals to 1 over 2 times the increase, which becomes -1, 2x minus 1 to the power -1 plus c, which again would simplify to 1 over 2 bracket 2x minus 1 plus c. I have skipped a step there. Last concept. So this one over here, we're focusing on these formulas here. If, and depending if, a value of r is 1, if the value of r is 1, we use this formula. And this component right here is very important. If, or when, ax plus b is greater than 0. So let's look at an example first. This is question 5i. There's an example for the other one over here, but I'm just going to go through this one up here. To find the general antiderivative, in this case, I know that x is going to be greater than 2/3. So I'm going to pick a number that I know is greater than 2/3, in this case 1. I know that if I substitute 1 into here, 3x minus 2, that would give me an answer that is positive. So looking back up here, I know that 3x minus 2 is going to be positive, which means I can address the formula above. It's going to be greater than 0. So this is the formula we're going to be using. Make sure you write that one into your resource book. Once you've got in, it's just 1 over the coefficient, ln, and then the function plus c. So in this example, it's just going to look like, and if I write the antiderivative of 2 over 3x minus 2 dx, it's going to equal to 1 over 3, because that's the coefficient, and then multiply by the natural logarithm of 3x minus 2 plus c. That's it. Hopefully that helps.